Okay, yeah. Regarding EDC, electronic device and circuits, we have four gentlemen over here. Vishwas Adhikari, Chandrakanta Jha, this Dekshant Dahal, Dinesh Ori. They are ready with DC motor speed control using PWM, that I think pulse width modulation, and direction changer using DPDT switch. And to witness their presentation, we have respected Bikal sir and sir, Kiran Bagale sir here to witness the project. I think now gentlemen will continue their presentation with the loud voice. Okay, please start.
Thank you, sir. Good evening, everyone. We are from 079 Batch Electrical Engineering Department, and today we are here to give you a short presentation on what we have done in our project. And the title of our project is DC motor speed controller using PWM and direction changer using DPDT switch. And my name is Vishwas Adhikari, and
I am Dikshant Dahal. I am Dinesh Ori and Chandrakanta Jha.
And now I will guide you through the overview of this project and give you basic idea what we have done in this project. And this project involves designing and implementing a system to control the speed and direction of a DC motor using pulse width modulation and a double pole double throw switch. Controlling motor speed and direction is crucial in various applications like robotics, conveyor belts, and electric vehicles for precise movement and functionality. Project objectives. Now I would like to describe you this. In number one, develop a reliable and efficient system. The primary goal of this project is to develop a reliable and efficient system for controlling the speed and direction of a DC motor. Achieve precise speed control. The system will utilize pulse width modulation to achieve precise speed control of DC motor. Enable reliable direction change. This project will also incorporate a DPDT switch to enable reliable and convenient direction change of DC motor. And now I would like to give a short presentation on how this works. And now I have turned on the switch, and when I use this switch, the speed increases as I gradually increase the potentiometer over here. And to change the direction by using the DPDT switch here, if it is in middle, it will stop, and if I change this to this direction, the direction will change. And this is what we have done. Now going on with the slide, circuit design. Now I would like to introduce what we have used, like components and software. First is a 555 timer chip, MOSFET, resistor, capacitors, diode, DPDT switch, soldering iron, a power supply, and the software and tools we use are PCB. For PCB layout, we use Proteus PCB design software, and for the physical components were soldered onto the PCB. Detailed circuit diagram. The circuit diagram includes a schematic showing of all components and their connections, including a 555 timer chip, MOSFET, resistors, capacitors, diodes, and the DPDT switch. The circuit diagram was prepared by using a Proteus software. The components were chosen as per their availability. This is the circuit diagram of our project, and this will be explained by one of our group members later on. And this was the output while we simulated the software. Now, after the simulation was done, we went on breadboarding, and then you can see on the picture that what we have done. While it was in breadboarding process. Now after that we move on to the PCB and kept all the components there and then soldered from behind, as in shown in the picture. Introduction to DC motors. We all have known about DC motors at this stage, so I think I don't need to explain about that. And to explain the pulse width modulation and motor speed control, I would like to give this time to Chandrakanta Jha.
Okay, Chandrakanta, you can explain from that side. Okay. Okay. Cover it.
Generally, if we use single switch, resistor, and LED, So to control its intensity, light intensity, if we continuously switch on and off our switch, the intensity of the light will see like if you see like that the intensity of light is decreasing as you continuously on and off the switch. So, but you can see that if we continuously on and off the switch, the pulse.
Okay. You can little bit. You can close up with that slide. Come little bit over here. Okay, now that's the right position.
Here you can see the pulse of our. If we physically switch on and off our switch from here, you can see the pulse like that. And if we switch on and off fast, much more faster, then this on and off process give the average velocity like this and this. This depend on our duty cycle. If our duty cycle here is the 50%, then if you see here is the peak voltage is 5 volt and average velocity comes to 2.5 volt. Here the duty cycle is 25%, so our average velocity comes to 1.25 1.25. But here the problem is we cannot do physically that much faster from us physical switches. So to overcome this problem, we have used here and MOSFET as a switch, and here simply we connected our gate, we connected our drain to the motor and gate to our battery supply, and the voltage modulation will be controlled from our 555 timer, which will be later explained. So it will normally what happens to that our 555 timer will vary the voltage, and from that varying voltage we will use a capacitor, and capacitor will vary it with the capacitor will vary the voltage by in relation with its charging and discharging time. Here we have used 555 timer, and the pulse like this square wave will be formed as our output wave. And so for further explanation, I would like to call Dixon for the presentation.
Thank you. So, as we already discussed about the pulse width modulation, basically what we are doing here is this NMOS acts as a switch, and to control the switch, we are using the output from the 555 timer. So basically, like this physical switch, we turn this switch on and off physically, right? To turn on the tube light and to turn off the tube light. But this MOSFET also acts as a switch, but we control that switch by the help of electronic signals, which will be generated by the 555 timer. So basically, this switch can turn on and off more than 1000 times a second. So that will help us to control the speed of our motor. So as he already explained about the pulse width modulation, it controls the voltage by varying the width of the pulses, and we can achieve speed control by the help of pulse width modulation. So it can also be used for efficient control of voltage, speed control, and also for voltage regulation. So the output voltage will be varied according to the width of the pulse. So basically, the working principle of our speed control circuit is based on the 555 timer, and the 555 timer generates the PWM signal, and that PWM signal will turn the MOSFET on and off rapidly, which will help us to adjust the speed of our motor. So now I would like to explain the circuit diagram in detail. Now the 555 timer IC is also included in the syllabus of our EDC course, so I would like to explain it in detail. So basically, this is the 555 timer IC, and this is the internal structure of the 555 timer. And Now, as you can see, the pin number 3 is the output of the 5-5 timer, which will generate the pulse. And we have connected the pin number 3 to the gate pin of the MOSFET, and the drain and source are connected to the power supply and motor. So this motor is connected to the power supply through the MOSFET. Now the pulse voltage will be generated from pin number 3, and accordingly the MOSFET will turn on and off. So now we have added these two resistors over here. So this resistor specifically, we have added this to protect the 5-5 timer IC just in case this MOSFET malfunctions and the current comes back to the IC. So to protect the IC, we use this resistor, and this resistor we have used to discharge the gate terminal of the MOSFET. So while switching, faster switching, some charges will be developed on the gate pin, and to discharge it safely, we have used this part. And we have also added this diode over here. So this diode basically is a flywheel diode, and basically it just it allows the current generated from the motor to safely go back to the another terminal of the motor. So basically, when we turn the fan off, then it will spin for some time, right? So until that time, it will generate some EMF, and consequently some current will be generated. So to safely discharge that current, we have used this diode. Now the 555 timer has three 5 kilo ohm resistors between pin number 8 and pin number 1. So the name 555 timer comes from the very fact that it has three resistors in series which act as a voltage divider. So basically the 12 volt supply that we have given will be divided into three equal voltages, basically 4 volts, 8 volts over here. So and then we have two comparators. Now the output of the comparator will depend upon the two inputs. So if the input in the minus terminal is high, then the output will be low, and if the input in the plus terminal is high, then output will be high. So the plus terminal of first comparator is connected over here, and the minus terminal of the second is connected over here, and the minus terminal of first comparator and plus terminal of second comparator are connected to pin number 2 and 6 respectively. So this is the basic working of a comparator as we have already studied. So if the output of the plus terminal is higher than that of minus, then the output of comparator will be high, and if the output of the minus terminal is higher, then the output will be low. Now the input of this minus the inverting input of this first comparator and the non-inverting input of the second comparator are basically short circuited. So if we supply one signal over here, then this signal will come to the plus terminal of second comparator. So basically in these two terminals we will supply same voltage from outside, and the voltage in the plus terminal of first comparator and minus terminal of second comparator will basically come from the inside of 5 timer. And the output of these comparators is connected to a flip-flop. So this particular flip-flop inside you used here is the SR flip-flop, and so the output here is Q bar. So basically when the S is high, S output is the input S is high, then Q will be high, right? So we have studied that in our electronics, basic electronics. So when S is high, then Q will be high. But in this case we have Q bar. So basically when S is high, then Q bar will be low, and similarly when R is high, then Q bar will be high. And if both the flip-flops are low, the input of both the flip-flops are low, then the Q bar will retain its previous state. So it will basically be high or low accordingly. So from the input of these comparators, it will generate one output which is connected to a flip-flop, and then the output of the flip-flop will be inverted over here, and it will be supplied to the gate pin of the MOSFET. So now it might be a bit complicated to understand, but this portion is in our EDC course also, so it will be beneficial if you try to understand it. So now I have a short example over here. So basically if we supply 3.9 volts at the pin number 2, then what happens is this first comparator will output high. because the voltage in the plus terminal is 4 volts. So it is greater than 3.9 volts, so it will output high. This second comparator will output low because the voltage in the minus terminal is 8 volts, which is greater than 3.9 volts. So this will be low and this will be high. So when S is high, then Q bar will be low, right? So the Q bar is low, then the inverting the low output from the Q bar, in pin number 3 we will get high. So basically the MOSFET will be on in this case. Now I am increasing the voltage from 3.9 to 6 volts, let's say. So when the voltage is 6 volts, then the output of both comparators will be low, right? So the flip-flop will retain its previous state and the MOSFET still continues to be on. Now the voltage reaches 8 volts. So in this case, the 8 volts over here, in pin number 2 and pin number 6, we will give 8 volts. And according to the second comparator, output will be high. Because basically when it reaches 8 volts and starts to increase a little bit, then output in the plus terminal will be greater than the 8 volts over here. So output of the second comparator will be high. And basically because of that, the Q bar will be high, and inverting that, we will get low output in the pin number 3. So the MOSFET will be off. So what we have done here is, when we supply voltage from 3.9 volts to 8 volts in pin number 2, then the MOSFET will be on. And when it reaches 8 volts, the MOSFET will be off. And then now again, if I decrease the voltage from 8 volts, then what happens is, both the input of the SR flip-flop will be low, so it will retain its previous state and MOSFET will still be off until it reaches 4 volts. So basically from 3.9 volts, starting from 3.9 volts to 8 volts, the MOSFET will be on. And if I again reduce the voltage from 8 volts to again 4 volts, the MOSFET will be off, and then again when it reaches 4 volts, again the output will be high. So this cycle continues. Now we have given varying voltage in pin number 2, right? So to get the varying voltage, one of the best methods is to use a capacitor. So the charging and discharging of capacitor will actually decide the output of the flip-flop, and consequently we can control the DC motor. So now to charge the capacitor, we have used 1 kilo ohm resistor over here, and we have used this 100 kilo ohm potentiometer, and then we have also, this is the charging path, right? So and then this is the discharging path connected to pin number 7. So through this path the capacitor charges, right? So from here it charges like this, and then from this path the capacitor discharges. So I will talk about that. So over here we have used 2 diodes, right? And this also is a diode, and these are also diodes. This is 1N4007 diode, and this is 1N4148 diode. So now we have used 2 different types of diode over here. So I have a question: can we replace this diode with this one? Anybody? So why we have used 2 different kinds of diode?
That you haven't explained yet. What kind of tires you have used?
Yes,
That's not elaborated.
Okay, I will
First you elaborate,
So
then
basically,
we will know the need.
the current handling capacity of this diode is lower than this diode, right? So, but the switching speed, basically, the response time of this diode is greater than this diode. So, basically, you might have understood. So right now, here, see, now in this path, there is a resistor, right? So current flows through the resistor. So that's why there will not be higher current in this path. But in this path, this motor will sometimes generate very high current, right? Basically, greater than 300 milliampere current can be generated over here. So this diode can only handle current up to 300 milliamperes. But this diode can handle current greater than that. So over here we have used this diode and this. But this diode cannot be used over here because this diode has a very faster response time in the range of around 2 nanoseconds. But this diode has response time in the range of microseconds. So we need faster switching. So for faster switching application, we have used this diode. Okay. So now this is the charging path, right? So through this path the capacitor charges, and then through this path the capacitor discharges. Now this pin number 7 is internally connected to pin number 1 via a transistor, and the base of the transistor is connected to Q bar. So basically when Q bar is high, this transistor will be activated and capacitor will discharge through this path directly to the ground. So I have a short demonstration. So right now the capacitor is charging, right? So the capacitor is charging, its voltage is increasing. And when it reaches 8 volts, it starts to discharge. Now after while discharging, the voltage again reduces, and then it reaches 4 volts. And when it reaches 4 volts, it again starts to charge. So in that way, the discharging and charging of capacitor will generate a square wave over here. So this pin number 5 is connected to the minus input, the inverting input terminal of the second comparator. So we do not need to change that. So we have connected this to ground via this capacitor. So this capacitor acts as a low impedance path for high frequency noise, right? So when the frequency increases, the reactance of the capacitor decreases. So the high frequency noise will basically go to the ground, and this pin number 4 is the reset pin of the flip-flop. So it is active low reset pin. When we ground this pin, the flip-flop will reset. So we do not need to control that. So we will connect this pin number 4 5 volt or the VCC. So basically, while charging, the output will be high. While the capacitor is charging, output will be high, and while the capacitor is discharging, the output will be low. So I have an animation. So when the capacitor is charging, the output is high. When the capacitor is discharging, output is low. So now capacitor is charging, output over here is high. The motor is on, and when the capacitor is discharging, output here is low, and the motor is off. So this is the basic circuit diagram of the 555 timer and our project. Now to talk about the calculation, I would like to call Zamadan.
So here basically recently explained that about the how our during the charging time our pulse width is high, and during discharge of our capacitor our pulse width is low, and about that how that high and low differs our motor speed. I am going to show. Firstly, I am going to explain its calculation. And here I wish to write or include that if we put our potentiometer wiper at 50%, you can see our R2. Yes, the R2 and R3 are equal that 50 kilo ohm. And our R1 is used as a 1 kilo ohm. Yes, 1 kilo ohm. And we have used 1 nanofarad capacitor, 1 nanofarad capacitor, and 10 nanofarad capacitor, sorry. And for our charging time, we have used this formula 0.693 into it's 0.693 into RC, and in our charging path, the RC is R1 plus R2 in series. And this formula came from V equals to V naught 1 minus e to the power minus T by RC, but we haven't mentioned it here because that's not our part of discussion. And we have basically used the values from R2 from here and R1 from here, and you can see that our charging time comes to 0.35 millisecond. Similarly, for discharging time, we have calculated our charging time 0.34 millisecond. And we know cycle time. Cycle time is the time taken by a wave or cycle to complete its one period or one cycle. So here our cycle time is normally the charging time plus discharging time, and it is 0.00069 seconds. And the frequency, this is the normal formula, frequency equals to 1 upon cycle time. And here's new term is introduced, duty cycle. Duty cycle is basically the cycle where our output is high, or when our output is on high. In digital logic we have studied about high or low. And this is the condition of this is the condition when we put our potentiometer at 50%, or if we kept our wipers at 50%. If we higher or lower, if we change our wiper.
I want to ask something. Chandrakant bhai. So what is Dinesh is going to do now? You are explaining calculation, isn't it?
This after, sir.
Okay, okay. Let's continue.
If we change our, if we increase our R2, our charging time will increase. If we decrease R2 and increase R3, discharging time will increase and charging time will decrease. It will affect our pulse width modulation directly. Here, if charging time will increase, our duty cycle will increase. And due to increase in duty cycle, our pulse width will increase. Pulse width will here while charging our pulse is high, and while discharging our pulse is low. And if our charging time is increased, our pulse width will also increase. And if the discharging time will be increased, our pulse width of loop will increase. It will cause simply, if high pulse width will increase, our average voltage will increase. If low pulse width will increase, our average velocity will decrease. Here we can use any other value capacitor, but remember, if we use high value capacitor, the motor will not rotate smoothly. If, for example, if we have used 100 μF capacitor, the cycle time will come to 6.99, which will cause in frequency 0.14, which will be very low. And if we see in simulation or hardware, with this frequency, our motor will stop. Our motor will rotate but not smoothly. Time to time it will take a jog or it stops for a fraction of a second. And here's the direction control working principle, DP/DT switch. That's also by part of presentation. DP/DT switch is very simple. If we know little bit about electrical circuit or electronic circuit, DP/DT switch is dual pole dual throw switches. In this you see this 6 points, and here the one terminal.
Chandrakant, एकछिन रोक्नु. भिडियो एकछिन रोक्नु.
अब सुरेश सरले पनि धेरै कुराहरू त भनिसक्नु नै भयो होइन. तपाईँको चाहिँ एकदम टु द पोइन्ट हुन पर्यो, अनि स्लाइड चाहिँ एकदम कम्प्याक्ट, अनि तपाईँहरूले अब स्लाइडमा नम्बरिङ पनि राख्नुपर्छ. कहिलेकाहीँ मलाई कुनै पर्टिकुलर पोइन्टमा चाहिँ तपाईँलाई चाहिँ क्वेसन सोध्न मन लाग्यो अथवा के क्युरियोसिटी भयो भने कुन स्लाइड भनेर भन्ने त होइन, एउटा स्लाइड नम्बरिङ भयो भने अलिकति बेटर हुन्छ. जसरी हाम्रो डकुमेन्टमा पेज नम्बर भए जस्तै स्लाइडमा पनि एउटा नम्बरिङ राख्न सकिन्छ होइन. अनि जस्तै अब आज तपाईँहरूले पिडब्लुएमको चाहिँ पिडब्लुएम सिग्नलले स्पिड कन्ट्रोल गर्छ भन्ने कुरालाई अलिक धेरै डेप्थमा जानुभयो. सिम्पल के छ, ड्युटी साइकलले चाहिँ स्पिड कन्ट्रोल गर्छ होइन. फ्यानको एउटा इनर्सिया हुन्छ, हाई भइन्जेल त्यो पावर्ड हुन्छ, पावर्ड भएपछि त्यो घुम्न सुरु हुन्छ. तर ड्युटी साइकल भने के हो त, कति पर्सेन्टेज अफ टाइम चाहिँ त्यो अन हुन्छ भन्ने कुरा त हो नि होइन. त्यो चाहिँ वेब फर्ममा चाहिँ हाम्रो जुन स्क्वायर वेबमा चाहिँ कति बेलासम्म अन हुन्छ भन्ने कुरा हो, फ्र्याक्सनमा हामी नाप्छौँ त्यसलाई होइन. अब अफ भएको टाइममा चाहिँ इनर्सियाले काम गरिरहेको हुन्छ होइन, अनि त्यसले चाहिँ त्यसरी स्पिड कन्ट्रोल गर्ने हो. हेर्दा त फ्यान घुमिरहेको जस्तो देखिन्छ, बट त्यसको पावर सप्लाई चाहिँ मोमेन्टरीली चाहिँ हाम्रो चाहिँ पिडब्लुएम सिग्नलले चाहिँ कन्ट्रोल गरेको हुन्छ होइन. त्यही भएर डिस्कसनलाई हजुरहरूले अझ मोर कन्साइज बनाउन सक्नुहुन्छ, नत्र तपाईँहरूको इफोर्टको त अब तारिफ नै गर्छु म चाहिँ है. ल अब बाँकीका दिनहरूमा अझै इम्प्रुभ गर्नुहोस्, अनि सबै टिम मेम्बरले एउटा ब्यालेन्स वेमा प्रेजेन्टेसन गर्नुहोस्. सबैलाई जस्तै स्ट्यान्डर्ड के हुन्छ भने प्रेजेन्टेसनमा तपाईँको 10 देखि 15वटा स्लाइड होइन, अनि 15 मिनट बढीमा टाइम लिनुपर्छ, खास रुल अफ थम है. अनि अब त्यसपछि अनि अडियन्सले इन्ट्रेस्ट भयो भने क्वेसन सोध्छ, अनि त्यसमा यु क्यान इलाबोरेट भन्ने कुरालाई चाहिँ मोटामोटी रूपमा 15 मिनटभित्रमा समेट्ने चाहिँ तपाईँले एउटा ट्राई गर्नुपर्ने हुन्छ है. ल, दिस इज माई सजेसन.
सर ओके सर.
तपाईँहरू पनि त्यस्तो साह्रो भन्नुपर्ने चिज मोस्ट अफ दि अब सबै कुराहरू सरहरूले नै लिइसक्नु भएको छ। अनि एउटा भनेको चाहिँ जस्तो अब यो जति म्याथमेटिकल कुराहरू छ नि तपाईँहरूले जहाँ आउँछ त्यो कुरालाई त्यही कुरा अलिकति त्यही नै रिप्रेजेन्ट गरिदिँदाखेरि पनि बेटर हुन्थ्यो कि म्याथमेटिकल टर्महरूलाई पनि होइन। जस्तो तपाईँहरूले क्यालकुलेसन देखाउनु भयो त फर्मुलाहरू ड्युटी साइकल आउँछ पनि यो हुन्छ होइन। तपाईँको जस्तो त्यो अन्पिरियड हामीले यसरी नापेको हो होइन, यसले यस्तो भन्न खोजेको हो। एउटा त पोइन्ट त्यही टाइममै भनिदिनु भयो भने त्यो सर्किटमा तपाईँ यत्रो टाइम लिनुभयो नि एक्सप्लेन गर्ने, त्यो अलिकति त्यहाँ रिड्युस हुन्छ कि जस्तो लाग्छ कि। अरू चाहिँ तपाईँको सरले भने जस्तै बाई नलेज वाइज तपाईँहरूले स्टडी चाहिँ राम्रै गरेर आउनु भएको रहेछ।
ल अब भाइको दिनेश भाइको एक्चुअली कहाँदेखि छ अब त्यो पर्फर्मेन्स चाहिँ उसलाई जहाँदेखि कन्भिनियन्ट छ त्यहाँदेखि गर है। सिस्टममा गर्न त्यो गर्न गाह्रो भयो भने सिस्टममा स्लाइड गऱ्यो भने भइहाल्यो नि। सिस्टममा चेन्ज गर्न असली पोइन्टरले गर्नुपर्छ भन्ने छैन।
यो स्विच चाहिँ
ओके ठिक छ। स्विचको बाबुको पार्ट थियो, बाबुले अघि पनि चाहिँ नि एक्सप्लेन गरिसकेको भएर र वी आर सर्ट अफ टाइम, त्यस कारणले गर्दा दिनेश भाइलाई चाहिँ अब तिम्रो कहाँदेखि छ बाबु यसमा जहाँबाट छ त्यहाँदेखि तिमीले स्टार्ट गर।
अगाडिको पनि हो डिपिडीको
ठिक छ, तिमीले तिम्रो आफ्नो रिहर्सलमा जे थियो प्र्याक्टिसमा जे छ त्यो चिजलाई चाहिँ प्रेजेन्ट गर कि यो तिम्रो युआर गिभिङ इक्जाम एज वेल नि दिनेश, बुझिरहेको छ कुरा। यु डोन्ट ह्याभ टु वरी, तिमीले चाहिँ कहाँदेखि आफ्नो चाहिँ प्र्याक्टिस गरेको छौ कहाँदेखि प्रेजेन्ट गर्न लाग्छ त्यो गर। भनौँ क्लास
I would like to call Dinesh for the further explanation for the experimental results.
I'm going to explain about experimental result. In our DC motor control, actually when we vary our duty cycle, then we can also change the speed of a motor. Duty cycle variation in pulse width modulation directly influence the average voltage applied to the DC motor. Now, as you know, higher the duty cycle, result the greater average voltage applied to the DC motor, so the motor of the speed increased. Likewise, when we lower the duty cycle, correspond to the slower speed. When we precise control over the duty cycle, the pulse width modulation, in pulse width modulation, when we vary the duty cycle, we can control speed of a motor. And for direction control, we use DP/DT switch. By using DP/DT switch, we can change the direction of DC motor by reversing the polarity. When you reverse the polarity, then the flow current reverse. So speed of a motor also reverse. Likewise, we use MOSFET. MOSFET they act as a switch. So it control the DC motor. Like overcoming challenges while doing our experiment or our project, some challenges were occurred. Circuit instability, address noise and interference issue through refined circuit design and shielding technique. We use capacitor there to reduce the noise. Component failure, implemented robust component selection, thorough management to ensure reliable operation. Design improvement, iterative modification to the original circuit need to enhance the performance and reliability. What we learned from this project is that we used breadboarding and then PCB design, simulation in Proteus. We learned about how to do that, and then real world application. What are the applications that we have to control the DC motor? In our robotics, DC motor are fundamental component for locomotion, manipulation and control. Control algorithm coordinate motor movement to execute a complex task with precision and efficiency.
by controlling the speed of a motor, we can manage the efficiency and cost reliability. And in our electric vehicles, DC motor is crucial in electric vehicles for propulsion. By controlling the voltage and current supplied to the DC motor, the speed, torque, direction of the vehicle can be managed efficiently. In our renewable energy system, DC motor plays a vital role, such as in our wind turbine, solar tracking system. By adjusting the rotor speed or solar panel orientation, DC motor optimize energy capture from renewable source. Control algorithm ensure that the system operates with maximum efficiency, enhancing the overall performance and output of renewable energy installation. Expanding the project. We can expand this project by wireless control also. When we use wireless control system, we can also control the speed of a motor. Implementing wireless communication capabilities will allow for remote monitoring and control to the motor system. We can also use microcontroller in our project for further improvement. And advanced feature implementing start stop real-time parameter monitoring and more sophisticated pulse width modulation technique will expand the project functionality. Key takeaway: pulse width modulation control. Precise motor speed control is achieved through the uses of pulse width modulation. We can control the speed of a motor by using pulse width modulation, as our member already explained. Direction control, we used DPDT switch, double pull, double throw switch for the reversing the direction of DC motor, overcoming challenges. Rigorous troubleshooting and iterative design refinement are crucial for reliable system performance. Future potential: the system can be expanded with additional feature and integrated component for enhanced capacities. Conclusion and future enhancement. Project summary. This project successfully designed and implemented a system to control the speed of and direction of DC motors. We know about it by using pulse width modulation and DPDT switch. The detailed components were discussed already. Future enhancement, future enhancement include addition feedback mechanism. We can also use feedback mechanism and integrating microcontroller, implementing remote control and expanding the system to handle higher power motor. And then lesson learned, we learn about insight for future improvement of our project and different troubleshooting and design modification. Like